Hello, everybody, and welcome back to my lecture series on sustainability issues in energy. I hope that you've been enjoying these lectures. I'm sorry there's been a little bit of a hiatus here between my previous video and this one, but we are back in action today. So today we're going to start our unit on geothermal energy. I think a lot of you are going to enjoy this. I know there's a lot of geothermal stands out there, so I think we're going to have a good time here. Today, we'll start our unit with a lecture on why the Earth is hot. This is fundamental to understanding the background for geothermal energy. So for Unit 3 on geothermal energy, I recommend a book by Stober and Bucher. It's called Geothermal Energy from Theoretical Models to Exploration and Development. I will be drawing on this book for a lot of the material that you'll see in this unit. It's very good, very well written, and I highly recommend it. Okay, so why use geothermal energy? Well, we talked for a long time in our unit on carbon capture, utilization, and sequestration about how to take carbon dioxide that is being produced by burning fossil fuels, get it out of the air, and then use it or put it somewhere that it can't escape back to the atmosphere. So that's one way of thinking about it. But rather than having to abate CO2 emissions, why not just use an energy source that doesn't produce very much carbon dioxide to begin with? So here's a plot of the equivalent CO2 emissions from power generation from various different sources. So on the x-axis, we've got grams of CO2 equivalent per kilowatt hour. And here are a bunch of different types of energy or excuse me, power generation that we're looking at. Okay, I guess if you want to be picky, kilowatt hour actually is a unit of energy, not power, but anyway. So you can see obviously coal is the most carbon intensive, and most of that, the CO2 emissions come from what's called fuel use here. So that's burning coal to power a steam turbine. Natural gas is less carbon intensive than than coal, but still fairly carbon intensive. But if you start going down here, you'll see two types of geothermal energy here. There's flash plants, which we'll talk about in a little bit, which do use a little bit of fuel and do emit some CO2, but it's a lot lower than what you get from natural gas or certainly from coal. And then enhanced geothermal systems, these deep geothermal systems, emit very, very little in the way of CO2 emissions. And most of that is just from running the infrastructure at the generation plant. So this is what we're going to be talking about in this unit, these geothermal types of energy sources. So what we do when we produce energy from geothermal resources is that we take advantage of the fact that the inside of the Earth is hot. Okay, so this is a cutaway diagram of what the inside of the Earth looks like, kind of. So on the very outer surface of the Earth, we have what's called the lithosphere. This is a rigid, brittly deforming layer. And below that, and the lithosphere is made up mostly of the crust, which is the outer hard layer of the Earth, and then a little bit of the mantle. So the upper part of the mantle, which is called the lithospheric mantle, actually deforms brittly. As we get a little bit deeper into the mantle actually deforms plastically by creep, and this is called the asthenosphere. So most of the mantle is contained within the asthenosphere. Then when you get a little bit deeper, you get to the outer core, which is liquid iron and nickel. And then there's the inner core, which is actually salt. Okay, so the radius of the Earth is roughly 6,370 kilometers. The mantle is about 2,900 kilometers thick. The crust is between 5 and 30 to 40 kilometers thick. I didn't actually mention the innermost inner core, which, for those of you seismologists, that that's actually a thing, but that's basically what it looks like. Okay, now what does the temperature profile look like as we move from the surface of the Earth to the middle? So right near the surface, the temperature increases very rapidly through the lithosphere and getting down to the base of the lithosphere into the asthenosphere. Then below that, it actually does not increase as rapidly. And we'll talk about why that is in a minute. And then we get down to the outer core, and there's even less of an increase than then when we get to the inner core, even less of an increase in temperature. But the center of the Earth is about 5,000 degrees Celsius, and the surface of the Earth is, right near the surface. You're averaging about 20, 25 degrees Celsius, just below the ground. So that's the temperature range that we're looking at. So we're taking advantage of the fact that there's a lot of heat in the middle of the Earth, and some of it reaches the surface, and we can drill wells and take advantage of that heat. So why is the Earth so hot? Well, there's really two reasons. So the first is that there's just a lot of leftover heat from the initial accretion of the planet, billions and billions of years ago. So that's essentially a gravitational potential thing. There's also a lot of radioactive elements within the Earth, most notably potassium, potassium-40, a couple of isotopes of uranium, 235 and 238, and then thorium-232. So this is a plot of the heat flux due just to radioactive decay over the entire history of the Earth, going back 4.5 billion years, okay? So you can see that, due to the nature of radioactive decay, the source term here decreases as we move forward in time, because the decay of those elements means that there's less and less of them around. So, but the total heat flux just due to radioactive decay today is somewhere a little bit less than 30 terawatts, okay? Now, if we look at the relative contribution of the three different radioactive species that we deal with, potassium is actually the lowest contributor today, and thorium and uranium are roughly equal. So that's what the radioactive elements give us in terms of heat flux. Now, there's two different types of heat transfer that we have to consider. So one of them is conduction, and this is simply the transfer of heat from hotter places to cooler places, simply based on the difference in temperature. Okay, so if you take a hot cookie sheet out of the oven and just set it down on the counter, it will cool off because the air around it is cooler than the cookie sheet. Okay, that's conduction. Convection is the other main mechanism of heat transfer, and this occurs because the medium that's conducting the heat actually moves. Okay, so you can think of this like, for example, if you've got like in a nuclear power plant, you use water as a coolant for the nuclear fuel. And the way that works is you bring cold water in, it passes across the rods and takes some of the heat away, and then it keeps moving and convects that heat farther downstream. Okay, with my cookie sheet analogy, you can think of this as if you took the cookie sheet, put it on the counter, and then had a fan blowing on it. That actually would be a combination of conductive and convective heat transfer. And in general, that's what we see. You typically don't have only one or the other. There's typically both that are occurring. So within the Earth, the temperature varies depending on the position. So we saw that. We looked just at a one-dimensional profile. But there's also some variation spatially that we'll talk about in a little bit. But the temperature over the history of the Earth has also varied in time, because the planet is gradually losing heat to space. Okay, so we've got variation both in space and time, so we can put these together in what's called the convection-diffusion equation. Now, this is a partial differential equation that relates the change in temperature over time to the spatial variability of temperature within the Earth. Okay, so this is the partial derivative of temperature with respect to time. This is just the derivative with respect to time, holding everything else constant. And in its most general sense, it's going to be the divergence of the product of the thermal diffusivity and the gradient of the temperature, minus the divergence of the velocity vector times the local temperature. Okay, so this is the most general form of the convection diffusion equation. Now I'm going to digress a little bit and we're going to talk about Lord Kelvin's estimate of the age of the Earth and come back to the convection diffusion equation. So William Thomson, later known as Lord Kelvin, was having a disagreement with Charles Darwin about how rapidly geologic processes happened. They were looking specifically at how long a particular chalk formation in England had taken to erode. Okay, so the year was 1864, and so using what they knew at the time about how the temperature within the Earth increases with depth, what Kelvin attempted to do was to prove that Darwin was wrong by calculating how old the Earth was. And so he could say, look, Charles, you're wrong about how slowly these things happen over geologic time. Okay, so here's what he did. So Kelvin went in there and he said, okay, let's assume the whole Earth is solid rock. We only have conductive heat transfer. And the boundary condition is that the maximum temperature at the center of the Earth cannot exceed the melting temperature of rock. Okay, so let's take those three assumptions. And we'll go back to the convection diffusion equation. So here it is here. So first assumption, we're going to say heat transfer only occurs by conduction. So this means that we're going to ignore the motion of the conducting medium. So your velocity vector is going to be 0 everywhere. So this term goes away. So we're just left with this term here. Now let's assume that our diffusivity is constant. So that means we can kick it outside the divergence term here. And if we're taking the divergence of a gradient of a single variable, that's just equal to the Laplacian. Okay, so we can say that change in temperature with time is just equal to the thermal diffusivity times the Laplacian of the temperature field. And let's work in one spatial dimension. So we're just considering depth. We'll call that Z. So we can say d temperature by dt is just going to be minus diffusivity times the second derivative of temperature with respect to Z. And I threw this negative sign in here because we're assuming that depth increases downwards, just to keep track of our sign convention, okay? All right, so the initial condition, we'll say everywhere initially the temperature was equal to the melting temperature of rock. We'll call that T0. The boundary condition we have is that the surface temperature of the Earth is going to be much smaller than T0, okay? And so small, in fact, that we're going to assume that the surface temperature is 0, okay? So let's let capital T here actually be the difference in temperature between the present day temperature and the initial temperature, okay? So with those assumptions, actually, we get a nice, pretty easy solution to the convection diffusion equation, which arises from the doing a similarity transform here, which is my favorite way of solving diffusion equations. And we end up with this term here. So it's the initial temperature times the error function of this group here, okay? So that's our easy solution. Now, we can work out the time scale for the cooling of the Earth by considering the geothermal gradient. So the rate of increase of temperature with depth is called the geothermal gradient, and we'll call that capital G. And we'll assume that at the surface, that is a constant value, okay, Z equals 0. So at Kelvin's time, they were just beginning to understand geothermal gradients, and this is how he went about it. So the geothermal gradient is the change in temperature with depth. So if we go back to this expression here and take the first partial derivative with respect to Z, I'm just going to tell you what that answer is. This is it, okay, for any arbitrary variable X. So if we specify that the geothermal gradient is the partial derivative, first partial of temperature with respect to depth at Z equals 0, we can come up with an analytical expression for this. So take the derivative of that with respect to Z, we come up with this. And then if we plug in Z equals 0, then this exponential term becomes 1. And so we just get this term here. So at any time, the geothermal gradient at the surface is going to be equal to this number here. And so if we know what the geothermal gradient is, then we can solve for the amount of time that it would have taken to reach that geothermal gradient, okay? So Kelvin the best understanding at the time was that geothermal gradients in 1864 were somewhere between 1 degree Fahrenheit per 100 feet and 1 degree Fahrenheit per 15 feet. Okay, that's a pretty wide range. It's almost an order of magnitude, but so Kelvin said, well, let's pick something in the middle. So 1 degree Fahrenheit per 50 feet, which is the same thing as 36 degrees Celsius per kilometer. Now, he then assumed that T0 was 7,000 degrees Fahrenheit or 3,900 degrees Celsius. And to be honest with you, I have no idea why he picked this. And if anybody knows, you can let the rest of us know, okay? This is way higher than the melting point of granite or basalt, okay? And I actually went back to his 1863 paper, and he just says, yeah, let's use 7,000 Fahrenheit because, that's generally what it's assumed to be, with no citation, okay? Obviously, the peer review standards of the day were a lot different than they are now. Okay, but anyway, that's what he started with. And then the thermal diffusivity, he just took a value of 1.2 times 10 to the minus 6. And this was just based on experimental data performed on rocks, okay? So if you plug all those values into this equation, you get a time of 99 million years. So Kelvin said, okay, look, the Earth is 99 million years old. We're done. That's how old it is. Now, we obviously know that that's wrong because our best estimates now from radiometric dating are something on the order of 4.2 to 4.5 billion years. So what did Kelvin get wrong? Okay, so later on, the discovery of radioactivity made some people think that it was Kelvin's failure to account for radioactive decay as an additional heat source that made him get the age of the Earth wrong. And Ernest Rutherford suggested this in 1904 at a lecture where Kelvin was present. There's a really great anecdote from his collected letters. He says, I came into the room, which was half dark, and presently spotted Lord Kelvin in the audience, and realized that I was in for trouble at the last part of the speech dealing with the age of the Earth, where my views conflicted with his. To my relief, he fell fast asleep, but as I came to the important point, I saw the old bird sit up, open an eye, and cock a baleful glance at me. Then sudden inspiration came, and I said, Lord Kelvin had limited the age of the Earth, provided no new source of heat was discovered. That prophetic utterance refers to what we are now considering tonight, radium. Behold, the old boy beamed at me. Okay, I first encountered that anecdote when I was reading The Making of the Atomic Bomb, Richard Rhodes' excellent book on that topic. But, this is a nice story, but it's actually not true. That wasn't the problem Kelvin had, okay? So if you run a numerical model based on what we understand about how much radioactive decay contributes to heat flux, the difference is very small. That's not what's going on here. Okay, so what I've got here, this is a nice paper by England et al., where they look going back over a geologic time. So here, this is 5 billion years here, right? 5,000 million years. And they look at the heat flux, or excuse me, this is the present day here. I think 0 is the start of the start of the accretion of the Earth. Anyway, so they look at how the heat flux would vary if you just have conduction alone without radioactive decay. So this is Kelvin's assumption here. And you can see when you include radioactive decay, okay, there's really very little difference until, you get, several billion years into the history of the Earth. And even at the present day, the difference that radioactive decay makes, it's like on the order of 10 watts per square meter, okay? One thing I'll note here is that heat flux, which we'll call little q, is related to the geothermal gradient by this constant kT, which is the thermal conductivity. So just so you understand what we're looking at here. But the point of this figure is that it's actually not radioactive decay that was the problem with Kelvin's assumption. It was actually something else. So John Perry in 1895 published a different estimate of the age of the Earth. So Perry was actually one of Kelvin's former assistants. And he assumed in his work that the interior of the Earth was liquid that actually convected, and it carried heat to the base of the crust. So in Perry's assumption, you've got a solid conductive crust overlying a convecting liquid. Okay, and then so you convect the heat up to the base of the crust, and then it gets conducted out to the surface. So this is, a highly simplified view of the interior of the Earth, but it's actually not that far off from what happens in the mantle to the best of our understanding now. Okay, so why does convection matter? Okay, so back to our convection diffusion equation. So this is the most general sense. So if we assume that the velocity is constant and we're only working in one dimension, we can recast this equation just in terms of one spatial dimension, like this. And again, remembering our sign convention where z increases downwards. What we can see is that if you include this term here, when the velocity is non-zero, that will act to make the geothermal gradient, it'll act to make the temperature change more slowly with time for a given geothermal gradient. Okay, so what this is going to do is it's going to get us a greater age of the Earth for a given geothermal gradient. So here's the math that Perry went through to prove this. So we'll assume that the Earth is a sphere and that the crust is extremely thin compared to the radius of the Earth. So the heat flux through the crust is going to be equal to the thermal conductivity times the temperature difference across the crust, and L is the thickness of the crust, which is very small. We'll again assume that the internal temperature is much larger than the external temperature. So the temperature change across the crust is approximately equal just to the interior temperature. Okay, so we can rewrite this just as interior temperature over thickness of the crust times the thermal conductivity, and that's going to be the heat flow. Okay, now the total rate of heat loss is going to be the heat flow multiplied by the crust's surface area. So we'll call that big Q. So change of big Q with respect to time. This is the surface area of the crust, and then this is the heat flow over here. So this rate of heat loss has to be balanced by the rate at which the interior of the Earth is losing energy as it cools. And so that's going to be mass of the Earth times the specific heat of the Earth, again, times this change in temperature with time. And so the mass of the Earth is simply going to be the volume of the Earth multiplied by its density, and then we'll just call this the specific heat. Okay, so this expression has to equal this expression at equilibrium. So we can make this equality here and then do some simplification. So we'll do that. We can cancel out a whole bunch of terms. And when we do that, we end up with a differential equation down here that we can integrate. Okay, so we'll integrate the left-hand side with respect to temperature and the right-hand side with respect to time. And what we end up with is that the natural log of the initial temperature is equal to this expression over here plus a constant of integration, where I've lumped the constants from both these integrals just into one constant. Okay, so here's our result, and the boundary condition is that the initial temperature was some T naught at time equals 0. So that means that the constant is simply the natural log of T naught. And so we can have this expression here and take the exponential of both sides. And what we see is that the temperature at the base of the crust is simply going to be given by this expression here. Okay. Now, the geothermal gradient is simply that temperature divided by the crustal thickness, again, because the external temperature is much lower. So we can write this equation here, and this tells us that the geothermal gradient is related to time by this expression over here. Okay, we can solve for time. We get this expression here, and then plugging in some values that we know pretty well. So let's assume crustal thickness is 35 kilometers. Radius of the Earth 6378 kilometers, average density 3,300 kilograms per square meter, specific heat 1,000 joules per kilogram per Kelvin, thermal conductivity is 3 watts per meter per Kelvin, and the initial temperature is 1,300 degrees Celsius, which is typical for molten basalt, with a geothermal gradient of 36 degrees per kilometer, which is the same one that Kelvin used. We get a time of 2.5 billion years. Okay, so this is much closer to what we now know from radiometric dating about the age of the Earth. So it actually appears that it was Kelvin's lack of accounting for convection and convective heat transfer that really steered him wrong. Okay, so what did we learn? Convection lowers the geothermal gradient, so the mantle convects, and as does the outer core, and that's why the geothermal gradient is rather shallow in both the mantle and the core. Convection in the outer core and mantle effectively transport heat to the base of the crust, and then it's conducted through the non-convecting lithosphere to the surface. And that's why the geothermal gradient close to the surface is much larger than it is at depth. And that is why the Earth is hot, and that is why we can drill down into the crust and extract that heat and use it as an energy resource. Now, it's obviously not quite that simple. There is actually a variation in heat flow around the surface of the Earth, and this has to do with the dynamics of mantle convection and plate tectonics. So here's a map of the globe here on the left showing heat flow, and you'll notice that the areas of high heat flow correspond to oceanic spreading centers. So this is where the mantle is very close to the surface, and you've got a lot of heat coming out. In areas where the crust is very thick, so some of these old cratons like in Canada, Scandinavia, places like that, Western Australia, you have very low heat flow because the crust is thick and it's very old and it's cooled off considerably. Even within the US, there's a difference in heat flow in the Western US, particularly in the Basin and Range areas and Yellowstone and some of those places. The crust is thinner, and so there's more heat flow. Whereas in the East, for example, the crust is thick, it's old, it's cooled off, and so there's a lot less heat flow. Notice some interesting spots here in Texas, which we'll talk about later. Okay, I hope you've enjoyed this lecture. I think it's been, hope it's been interesting to you. Next time, we're going to start getting into the nitty-gritty of how geothermal energy works, and we will start talking about heat pumps, which I know many of you will be excited about. Okay, well, thanks for coming. I hope to see you subscribing to the YouTube channel and come back for some more videos in the future. We'll see you next time.